Hello everyone, and welcome to this new and exciting session in which we are going to look at post-training quantization with TensorFlow. In the previous session, we looked at quantization aware training still with TensorFlow, and now we'll look at how to do quantization for a model which has already been trained. Now, as you could see here, we have this pre-trained model which obtains an accuracy of 84% and a top 5 accuracy of, or rather top 2 accuracy of 95.6%. And then in the section, we'll quantize this model, check out on whether this quantized model occupies less space as compared to the original model, and then also verify that not much model performance is lost. Before we start with the quantization process, we should note that we are going to be using this TensorFlow Lite library. Now, this TensorFlow Lite library is a mobile library for deploying models on mobile devices, microcontrollers, and other edge devices. So this means that in these environments where the compute resources are limited, it's important for us to quantize the models, since we will now get smaller and lighter models and also faster models. Here we have a general overview of how this works. You will see you pick a model, like for example efficient net based model, convert this model to TensorFlow Lite using TensorFlow Lite's converter, which we're going to see shortly. We then deploy this by taking a compressed version or a compressed TFLite file. Now, we were already working with, for example, Keras files, which are HDF5 files. Now this TFLite is some sort of compressed file, and this compressed file will be loaded in the environment in which you'll be working in. And then from here, we'll also quantize this from 32 floats to 8-bit integers, which can run on devices with low compute resources. So here in the documentation, we have here TFLite and you have TFLite converter. Basically, this TFLite converter, as the word goes, is going to convert your models into the TFLite format. And here, as you can see these examples, you have this TFLite converter from a saved model, from a Keras model, from a function, from a GX model. So let's say, for example, we work with a Keras model. We just have the model passed here, and then you generate this TFLite model from this model, making use of this TFLite converter. Now, apart from this arguments, we also have the attributes. So here you could specify the optimizations, the representative data set, which is very important in the case where we're working with static quantization. Remember that with static quantization, we have to obtain the scale and 0 point values by making use of unlabeled data. So basically, as we had seen previously, all we need to do is to pass in the inputs, which in this case are images, and then these values will be inferred from the model's interaction with the inputs. Then we have the target specifications, inference input type, inference output type, whether to allow custom operations or not, and then whether to exclude the conversion metadata or not. So that's it. That's our converter right here. Now we paste out this code from the documentation, and then let's take this first here. Now we'll apply some of the attributes that we have. This converter dot optimizations. Let's get back to the documentation, the optimizations, and here we could set this optimization with this TFLite optimize. So let's open this up. There we go. You see this takes different values. We have default, whether we want to optimize for size, this is deprecated, does the same as default. Optimize for latency, does the same as default. This one is experimental, hence subject to change. So what we're going to do here is simply take this default. So that said, we have the TF.Lite optimize and default. just as we had in the documentation right here. Now we could also specify the inference input type and the inference output type. So let's get back here. We have, there we go, converter, inference input type is gonna be unsigned int 8, and then let's copy paste this. We have the output type, which is going to be the same. So that's it. So we'll specify this, the inference input type and the inference output type. And now let's specify the representational data. So this representative data set right here, which in fact is a generator which permits us output the input values, because recall, all we need in the static quantization is just these inputs. So here we have the generator which yields the inputs, and then here we'll just say converter dot representative data set equals the representative data generator. Here we have our training data set. Now we could take we could take all our training data set, or just a few. We obviously don't need to take all the data set, so we could just take like 20 and use that to obtain the values for the scale and the 0 point. Now if you new to this notion of scale and 0 point, it's important you check our previous sessions where we treat this. So let's run this here. We also run this, and now we set to convert. Oh, this model here is pre-trained, our pre-trained model. So let's run that, and that should be fine. So we now set to carry out the conversion. Now we're done with the conversion. We are now going to save this in the TFLite format. So we have this path, and this path we are going to have this file. So let's run the cell, and that's fine. So we get that we have the file size here, and when we check this up, you see we have this 21 megabytes. So we're going from this model, which we could check out here. We're going from this model, which is 90.7 megabytes, to a 21.12 megabyte model. Now, before moving on, we should note that if we want to implement dynamic quantization here, then we wouldn't specify this representative data generator. So that's it. Let's get back. We install this TensorFlow Lite runtime. Now, talking about installing the TensorFlow Lite runtime, once we already have this TensorFlow Lite file right here, if we want to run this in some other system, say for example want to run this in our Raspberry Pi, all we'll need to do now will be to install this runtime, and that'll be it. We wouldn't need to install TensorFlow any longer. So we just have this, we run this, that gets installed, we import the TFLite runtime, then we prepare our test image. So we just run this. We've seen this already. We have our pre-trained model, we're gonna get the argmax and then the corresponding class. So that's it. We should get angry. See, it matches with what we expect. We could try out this other example here. Let's run this, and there we go. So this is our model. Now we're going to use this runtime to run our TensorFlow Lite model. Now we've restarted the session, and you'll see that without TensorFlow, let's do this. Let's say TF zeros and 1/2, for example. We run that, and you see this is not defined, so we have no imports for now. Now let's take this off, and then we get back up here. We install our runtime, import the runtime. I think we'll be needing NumPy. So what we'll do is we're gonna take this NumPy. So we're trying to work without necessarily needing TensorFlow. So we have this imported as NumPy. That's it. Here we have this test image, OpenCV. So we would import CV2. That's fine. Well, here we make use of TensorFlow. but we will see how to get rid of this dependence on TensorFlow. So first of all, here we have to note that TensorFlow was used here to convert this test image. Here, let's print out our test image. To convert this test image, which is an unsigned int with 8-bit. So here, let's do this. You see, it's an unsigned int. We wanted to convert this into a float, and that's why we made this change here. So here we wouldn't need this any longer, and here we could use numpy. So we have that, and everything looks fine. Okay, so we have this test image, and that's fine. So now let's run this, and we have our image. Now image not defined. Let's get back here. Oh no, this is the test image. Test image. Run that again. This should be fine. Okay, so we have now our image, and then here we see we have this interpreter which loads our TensorFlow Lite file, which we've saved in the drive, and then we allocate tensors. Once this is done, we move on to get the details, the input and output details, which we had from the conversion process. Now here we have the unsigned int, and here we also have the unsigned int, and then you would see that we have this test image which we will change the type. So first of all, you notice that this image is turned to a numpy array, which we don't need any longer because it's already numpy. And then even this type, we do not really need to do this. Although if you print this, let's comment the section, and if you print this input details and we get the data type, you will see that we have an unsigned int. Now TF not defined. Well, here we will use the TFLite. So let's have this, run that again. We have TFLite runtime has no attribute interpreter. Now what we'll do is we'll have this dot interpreter. Okay, so we should have this, and this should work now. Okay, that's it. Now we have this, we run this again, and that's fine. So you see we have, you see, the unsigned int, which is what was expected, because when doing the conversion we have specified that we wanted this data type for our input and our output. So that's it. Let's take this off. What we're saying is we don't necessarily need this step right here. So this would have been useful if we had this as a TensorFlow tensor, and if we did not have this as an unsigned int already. So now that we have that, you see we set the tensor. So here we have our test image. That's it. And then the input details index, you could print this out so you see what's in here. Input details index, as you could see, it's 0, though now in this line we're getting an error. We got 3 but expected 4 for the input. So let's get back here. Okay, here we had this change to im. Let's get back. So what we're saying is here we have this expand dims to get from 3 dimensions to 4 dimensions, and the name was still im. So let's have that. We run this again. Here we have our test image now, which has 4 dimensions, and then now this should work. So here we set the tensor, and then we run the inference. So that's it. We run the inference here, and once we run the inference, we should be able to get the tensor at the level of the output. So let's take this off and then run this now. Takes a while. Yeah, this is the inference process. Now it should be noted that TensorFlow Lite has been built for mobile and embedded CPUs. So general purpose CPUs like this collapse CPUs aren't the best match for TensorFlow Lite models in terms of speed. Now we print out the output, or we could just let's print out the output, see what's in there. See, there we go. It shows that we have this here, the highest value. Then we could do np.argmax of this output right here. Run that again. That's it. Now let's take this here so we could get the class name automatically. Then now let's run this and we get the class happy. So this is what we expected. And again, we've done this without having to import TensorFlow. So we didn't need TensorFlow once we already had our TFLite model. You could see here, TF not defined. Now our next step will be to measure the accuracy of our TensorFlow Lite quantized model. So here we do exactly the same process as we had before. We basically have the model path, and then this input details, output details, and then we go through our validation data set. Take 100 elements in our validation data set. So this means that we would have to import TensorFlow for this process, since we are trying to evaluate the model's performance. So here we have this. We will need the validation data set. So we'll need to get back and run this cells here. So let's get back here. We will run this. There we go. We will run in all the cells. Now when we want to import this, when TensorFlow is already imported, we get in this error. So what we'll do is we'll just have this here. We run that. There we go. And then when we get to this accuracy, you will notice we use the TensorFlow Lite. So it's TF.Lite, not TFLite. So we're using this model from TensorFlow and not from this package which we had installed here. So that's set. Now we have that set, our accuracy. We have input, output, as we were saying, our validation data set, test, image, which is going to be passed here, the inference. We get the output, we compare. If they're the same, we increase accuracy. If not, we skip and then we move on to increase the total. And then from here we have accuracy divided by total, or let's say positives divided by total, or let's say correct, yeah, correct predictions. So let's change this to correct. So here we have correct predictions, and that should be it. So we have this accuracy here, and then we specify the model path. Let's get back here and then take this path of our TFLite model. Now we have simply accuracy, and then we specify that path. Okay, let's have this and we run this now. There we go. We're done with computing the accuracy for our TFLite model, and we get 0.82, that is 82%, as compared to the 84% with the original model. Now to get a more accurate value for this, it's advisable to use the whole data set. So you could take this off, and so now you have your model which performs at 82% accuracy, and which now could be deployed in some mobile device.